Are there any questions from the worksheet?
Could you go over question 8 and 9?
Yes.
Thank you.
Okay, so a string can withstand a force of 135 newtons before breaking. A 2 kilogram mass is tied to the string and whirled in a horizontal circle with a radius of blah, blah, blah. What's the maximum speed that the string can be whirled before it breaks? So if, let's just say we have a string and we're twirling in a circle. I don't really want to use pink. Let's go blue. Then the tension is going to be the FC. Okay. Now, if we can have up to 135 newtons, we'll make that, and then this is going to be like, so tension is our FC, so FC will equal 135 newtons. And then we can use this formula, mv squared over r, to see how fast it's going when it's 135 newtons. So let's just solve that. So that just becomes 135 equals 2 times v squared over 1.1, and v equals 8.62. So if you look at the formula, anything more than 8.62 means that FC will be higher than 135. Okay, because 8.62 is a numerator, so the bigger it gets, FC is going to get bigger. So that means by setting the FC at our maximum force that we're allowed, you're finding the maximum velocity that can work. So that's all you're doing. You're just setting your maximum FC and then finding the maximum velocity. Number 9, cars traveling around an unbanked curve. What is the maximum speed the car can go before skidding if the coefficient is 0.95? So it's unbanked, therefore FF is going to be mu mg because it's flat ground. And so we can find the maximum friction with 0.95. So that's going to be 0.95 times 932 times 9.8. And so that's going to be 0.95 times 932 times 9.8. 8,676.292. And again, when you have a car going in around an unbanked corner, it's the friction that's causing the FC. So in this formula here, FC equals mv squared over r. You can just put that in 8,676.92 equals 932 v squared over 82. Okay, good. And that gives your maximum velocity that you can round the corner with. Okay, and then the same for B. So again, all you're doing is you're using, like, I guess you can call it an upper limit, right? You can have a force up to a certain point, and anything less than that. So any speed less than 28, it's actually 27.6 or whatever. So technically it's not 28, but any speed less than that means that your FC is going to be smaller than the friction, and that's fine, because if you think about your curve, this is your FC right here. Anything smaller than that is okay. Anything bigger than your minimum amount of force going this way, it means that you have force going that way. Okay, and then you can't round the corner. So all you're doing is setting the maximum. Okay, any other questions? Okay. So we kind of touched on this yesterday, some of this. Let's look at problems that are going in a vertical circle. Okay, so we have a mass being on a string being spun in a vertical circle at the top and the bottom of its path, and we're going to draw the forces acting on it. Okay, so at the top of the path, you have the tension in the string and the FG going down. And then at the bottom of the path, you have the tension going up and the force of gravity going down. Okay, and as with any object moving in a circle, there is a net force acting on it. And because net force in a circle is actually centripetal force, we can also put centripetal force. So this net force is the centripetal force. So notice at the top of the arc, the centripetal force is, so technically at the top, the FC is going down, okay, going towards the center, so it's going down. So at the top, it would be negative FC equals negative FG negative T. And so we'd say FC, I wrote FG here, equals FG plus T. And at the bottom of the arc, FC is going up. So FC is positive equals positive T minus FG. Okay, so it's a different net force at the top than it is at the bottom. Now, if you have ever spun anything in a vertical circle, like a bucket full of water, or something on a string, you'll notice how it tugs the most at the bottom. Okay, so at the bottom, tension is maxed. Okay, so it's the strongest, it's the highest at the bottom, and it's the lowest at the top. So let's do an example. We have something moving in a vertical circle. We have the period. What is the tension in the string? So at the top of the arc, we're just going to use what we had before, FC equals FG plus T. So that's those two, T and FG. And so for the FC, I'm going to be using m 4 pi squared r over t squared equals mg plus, and now I'm going to change this to ft, because if I just use t, I have capital T over here for period, so now I have to change it to ft. I know it gets confusing. Okay, so 1.7 times 4 pi squared times 0.6, that's 2, 6, over 1.1 squared equals 1.7 times 9.8, that's FG, plus FT. Okay, and then we can solve that. So 1.7 times 4, oh, stupid pi button, pi squared times 0.6 divided by 1.1 squared, and then minus 1.7 times 9.8, and you get FT equals 16.6 newtons. Okay, and at the bottom, we have tension going up and FG going down, and so this one's going to be FC equals FG, sorry, FT minus FG. And so it's going to be the same FC. Okay, that's dependent on mass and pi and r and t. So this is still going to be 1.7 times 4 pi squared times 0.6 times 1.1, or divided by 1.1 squared, equals, now instead of going FG plus FT, it's FT minus 1.7 times 9.8. So now we just go 1.7 times 4 pi squared times 0.6 divided by 1.1 squared. And then we're going to add 1.7 times 9.8. And you get FT is equal to 49.9 something. So it's just call it 50 newtons. Okay. So you'll notice how the tension is stronger. It's bigger at the bottom than it is at the top. Okay, and that's because you're fighting gravity as well. This is a lot easier in class when I can actually spin stuff from a string and have you spin stuff. But part of your homework is to go outside and spin something. Go for it. Also, maybe like when you were a kid or not, you filled a bucket with water and spun it like in a vertical circle and noticed that the water stayed in the bucket. Okay, you should be able to explain why that's the case now. Can anyone tell me why the water stays in the bucket? I'll give you a hint. Here's your hint. Okay, it's centrifugal force. So if you imagine a bucket of water, so here's your bucket, bucket of water at the bottom, and you're spinning it in an arc like this. At the top, because it's spinning this way, the water isn't allowed to fall because the water's going this way. Okay, it's not going to fall if it's moving in a different direction. And so because of centrifugal force, the water does not fall as long as you're going fast enough. Okay, that's why. Kind of an interesting tidbit. Now you can tell your friends, hey, check this out, and then explain why. That's how you become a nerd. Okay, now suppose the mass is spun with just enough speed to keep it moving a circular path. Okay, so technically at the top, at the minimum speed you need, tension can be 0. Okay, so there is a speed at which you can swing this when because your FC at the top is equal to T plus Fg, you don't need the tension. Fg is enough to cause centripetal force. And so at the top, at a minimum speed, tension can be 0. Okay. Now, if that happens, we say that the mass at the peak of the arc is weightless because the net force working on it is only Fg. Okay. And so this is the same as an object in total free fall. If I wrote F net equals Fg and asked you, what is this object doing? Well, if you drew that free body diagram, that's what it is. Well, what's that object doing? That object's flying straight through the air. Okay, it's falling, it's in free fall. Well, that's the same thing as what we're doing here. If I say Fc equals Fg, this is the same thing as net force. The only difference is that it's moving in a circle, but it's still weightless, okay? And this goes into, you have to remember that like technically, if you have a mass that's sitting on a scale and you have Fg and Fn, this is the weight. Okay, it's Fn that is weight. It's not Fg that's weight. Fn is weight. So if Fn is 0, it's weightless. Okay, and that'll become important when we talk about like roller coasters and stuff like that. So an object is swung in a vertical circle with a radius of 0.75 meters. What is the minimum of the speed of the object at the top of the motion? So the minimum amount of speed is when tension is equal to 0. So tension is equal to 0, and the only force acting on it is Fg. So then we would say Fc equals Fg. And then we want to know the minimum speed, and we have the radius. So this is going to become mv squared over r equals mg. Now notice how the mass doesn't matter. We can just get rid of it. And then solve this for v. If you solve it for v, you get v equals square root gr. Okay, and that will always be the minimum speed. Regardless of what the object is, it'll be the minimum speed required to be in a circular motion. So if we solve it for this one, 9.8 times 0.75. Forgot a bracket. 9.8 times 0.75 square root. So this particular radius, you would need 2.7 meters per second. And keep in mind that that's the average speed, right? If you go 2 pi r over t, that's your average speed of the circle. But it's also the constant speed you need at the top. So you have to be going 2.7 at the top in order for it not to fall. Anything less than this, so anything less, the object falls at top. Okay, so if you try to swing something really slowly at the top, it's going to start to dip. Okay, it's going to fall, and it's not going to stay in its circular path. Okay, notice that the velocity of the object, I don't know what these are supposed to say, doesn't, depend on mass. Depends only on radius. Okay, g is constant, so it's only radius. So in order to find the minimum speed of anything in a path, you just go v equals square root gr. Okay, so it's kind of a special case. And this is on your formula sheet as well. I typically, well, I once took it off because too many people were relying on it to solve just normal velocity, and that's not good. It's only in a special case of finding the minimum speed. Okay, that's the only time you can use it. And I mean, it's not hard to derive. So if you understand this part, then you don't even have to memorize or use that formula. Okay, any questions about vertical circles? Okay. Now, up until now, all of our curves, when a car goes around a curve, it's been unbanked. Now, we're going to make it banked. So if you notice that, like, if you exit a highway or enter a highway, you're going on the off or the on ramp, those ramps curve and they're banked. They're at an angle. Okay, I don't know if you've ever been to, what's that arena in Burnaby? They have that cycling track around it. And like, you watch cycling on TV or in the Olympics or something like that, and you're like, oh, that's kind of cool, whatever. But you actually see the track in real life, it's like almost vertical. Like it's so banked, the angle is crazy. And that's because they're relying on the bank to travel in a circle. So let me explain why banks aid in circular motion. So remember that we have FG going down. Oh, let's put it this way. FG going down. And then FN goes up this way. Okay. Now, in order for this object, you can't just picture it like as we did on an incline. So when we did inclines, we had an incline, an object on that incline, and it would slide up or down. Okay. This isn't sliding up or down. It's going into the page. Okay, and rounding a corner. So it's not, you can't just view it as a normal incline. Now, if it's traveling around a corner, there has to be an FC, okay? And that FC is going this way. Okay, so we're going to call this FC. Now, on a frictionless corner, so there's no friction here, only FN and FG act on the car. Now, in this case, if the object, because it depends on the actual motion of the car because it's traveling in a circle, the FN is larger than the FG because it both matches FG and causes FC. So if your FC is going to the right, let me move this Fn, and Fn is bigger, then if you break Fn into components, you have this component right here, which is Fg, and you have this component right here, which is Fc. Okay, so this line right here is Fc. Okay, and so the deal is, if you add them together, Fn plus Fg, and in this case, that would look like this, Fn plus Fg equals this line right here, which is Fc. And so it has to equal Fc. Fn plus Fg equals Fc. Okay, now on an incline, remember that Fg was bigger than Fn because Fn was a component of Fg. Okay, so we had Fg going down, Fn going that way, and this component of gravity right here was your Fn. And that's because it's not traveling in a circular motion. So you have to understand that because it's traveling in a circular motion, because there's this Fc here, Fn is actually bigger than Fg. Okay, it's kind of tricky. Okay, so let's do a couple examples. Calculate the angle at which the frictionless curve must be banked if a car is around to round it safely at a speed of 22 meters per second if its radius is 475 meters. So let's say it's banked this way. Okay, we have our Fn, Fg. So we're going to go Fn, Fg, and that is equal to our Fc. Now, in terms of angles, think about this angle of the arc right here, okay, of the incline. This relationship here, where like this angle right here between Fg and Fn is still the same thing as it was before, where this angle right here was the same thing. Okay, and remember from inclines, I don't know where that I put that, but we had our Fg going down, our Fn going that way, and then our Fn or Fg perpendicular, let's say, and that was our incline. This angle was the same as that angle right there. So the angle forms between Fg and Fn. Okay, that's the angle of the curve right there. Okay, so that's what we're trying to find right here. Now, in this case, we're going to have, because we have our speed and radius, we can find our Fc. Okay, and our Fc is going to be, actually, I don't want to do that yet. Okay, so we're going to be able to find our Fc because we have V and R, but we don't have mass. But that's okay because Fg is mg and Fc is mv squared over r. So with no mass, it doesn't matter because we're going to have to cancel out the mass in some way. Okay, so let's relate both of those using trig. And so Fn is our hypotenuse, and so we're dealing with tan. So tan theta will equal Fc over Fg. Okay, and then we can put in our formula. So tan theta equals Fc, which is mv squared over r, over Fg, which is mg, okay. Now, this is a compound fraction. So if you think about pre-calc 11, mv squared over r times 1 over mg. Okay, remember you multiply by the reciprocal. And the masses will cancel out, and you're left with tan theta equals v squared over gr. Okay, and then we can just plug in our values. So tan theta equals 22 squared over 9.8 times 475. 22 squared divided by 9.8 times 475 equals 0.10, and then I'm going to second tan that, and I get theta equals 6 degrees. 5.94 degrees, so 6 degrees. Okay, hopefully that makes a little bit of sense. So we're using the relationship where Fn plus Fg equals Fc. Okay. Now it doesn't always have to be Fn. So we have a toy plane attached to a string so that it flies in a horizontal circle. So if you can imagine that this plane would just be hanging, but if you throw it in a circle and it just keeps going, like there's like a propeller here. I actually did this in my classroom once. I hung up a plane with like a battery operated thing and I did it in a circle and it just kept flying in a circle. So in this case, if we're going to draw the forces acting on the plane, and you can draw this anywhere in its circular motion, but let's just choose, it's drawn right here. So let's just choose this point right here. We have gravity going down. We have tension going this way. Oh boy. Okay, tension in the rope. And if you look at those two, you think, oh, if I add those two together, tension plus Fg, I get this, which is Fc, right? Fc is pointing towards the center of the circle. Okay, and it works the same way if you do it on the other side, because the tension would be going up, Fg going down, Fc would be going that way. So it works anywhere you draw it. Okay, now this angle right here happens to be 28 degrees. That looks like a weird X tension. So now we need to look at our information. So we have the mass, we have the radius, we have the angle, and we're trying to find the period. So that means if we're trying to find period, we have to have a formula that has period in it. So we're going to be using Fc equals m 4 pi squared r over t squared, because we're trying to find the period. We don't know the tension, but we know the mass of the thing. So again, we're going to relate Fc and Fg. So tan 28 equals Fc over Fg. So it's going to be m 4 pi squared r over t squared over mg. And again, we're going to be able to cancel out the masses. So it's going to be tan 28 equals 4 pi squared r over t squared g. I think that's the easiest way to do it. And then we need to find our t, so we're going to move that over cross multiply. So t equals 4 pi squared r over g times tan 28, and then square root that whole thing. Oh man, loaded question. Okay, so 4 times pi squared times r, which is 0.8, and then divide that by 9.8 times tan 28, and then square root that, and we get t is equal to 2.5 seconds. That seems like it's a really long time. Let me double check my answer. Whoa, what did I do? 4 times. What the heck was that? Oh, I hope I didn't just change my calculator. Okay. Times 0.8. Yeah, that's the right answer. Okay, so those are your banks and angles and stuff. Any questions about those? Is anybody like super confused right now? Maybe. Okay, in terms of the worksheet, you can work on 5.2 now. Let's see how far it goes. Yep, just 5.2. And then I'm going to work on interim reports, but I'll probably be done pretty quick. So it's 9 o'clock now, so maybe at like 10:15 or 10:30 or something like that, we'll do the next lesson on gravity. In terms of the outlook for this course, I think we might actually finish electrostatics and electromagnetism. So that's pretty good. Well, we're gonna try. We're gonna hit electromagnetism. We might not finish it, but I think we're gonna get close. So hopefully we can do those things, because it'll help you in university. So okay, that's it for now. So I will work on interms. I'll send those out as soon as they're done. Don't forget about, I'll message you in your interim to show your parents that one file that I post. So that's it for now. So I'll see you guys in a bit. And again, any questions, just ask.